let's talk about magnetic particle magnaflux inspection. Now, magnaflux is a trade name. However, you get kind of lazy and start to refer to every kind of magnetic particle inspection as magnaflux, but the real term is magnetic particle inspection. And again, this is another form of non-destructive inspection that we like to use for ferrous parts, meaning they contain iron in the metals and can be magnetized. This can range anything from cast iron to steel parts, you name it. As long as it is capable of being magnetized, we can get an indication. Now you'll notice this is a pretty complex machine as we take a step back and look here, and you'll also notice that it has a very large panel coming off of the electricity. The reason for that being is we use a lot of current to magnetize parts. So let's take an example. We have our camshaft right here. This camshaft is made out of steel, and we want to inspect it for cracks that would not be apparent to the eye. Now, one of the differences with magnetic particle inspection as opposed to, say, dye penetrant is we actually have the ability to see internal cracks with magnetic particle inspection because of how the flux lines form. Effectively, we can either form a magnetic field running longitudinally down the part or in a transverse direction around the part, and that's going to allow us to see different cracks. So if we want to see cracks longitudinally running front to back, then we need to use our circular coil here to run current around the part or in a transverse direction to get longitudinal cracks. The reason for that being is that the magnetic lines of flux are going to form 90 degrees to the flow of current. So if current flows around the part, 90 degrees is going to be down the longitudinal axis of the part. On the flip side, if I want to see transverse cracks, meaning are running around the part, then I will put it in the headstock here, and we're going to run current directly down the part longitudinally to form those flux lines. Any interruption in that magnetic field caused by, you guessed it, a crack or a flaw in the part is going to attract stronger lines of flux or a disruption in that field. What we do once we've magnetized the part is we have a solution here, which is basically kerosene with very fine iron particles mixed in that have been treated with a special fluorescent dye. So we can use this nozzle right here. We bathe the part in that mixture, and the flux lines will attract any iron particles. So if we have any disruptions, it'll hang on around those cracks to the iron particles draining over the part. And when we put a black light to it, we can see where those iron particles have collected. So the way that this works, if we were going to do what we call a headshot, which is running through the headstock, we load it up into the machine by putting this in position, and we're going to turn this crank the correct direction to get a nice tight fit. And we have a foot pedal down here which controls our headstock. We have a pneumatic chuck there as well. We're going to tighten down our headstock, and now it's firmly held in place. So normally if this machine is on, it's going to make quite a bit of noise because of the pump that circulates all of this mixture around that we're going to bathe the part in. But for the sake of demonstration, I'm going to leave it off for now so you can hear what I'm saying. When the part is set up in the stock like so, we're going to set up the machine for the jolt of electricity. Now, the way that this works is we take a look at our control panel here. Here's our control for the pump. Here we have a switch that lets us select alternating current or direct current. Now, if you've covered basic electricity, you'll understand that when we try to magnetize a part, we need to use direct current. Effectively, because the current is running in the same direction through the part, it's going to allow those iron particulate pieces, those molecules inside the part, to form a bias, which gives us a magnetic pull. If we need to demagnetize a part, we use alternating current. The reason for that is that if we switch our current back and forth, it's going to cause those molecules to lose their bias or lose their polarity, and life is good. So if we're magnetizing a part, we set ourselves to DC. If I'm using the headstock and tailstock to run current longitudinally through the part, I'm going to have it on the contacts setting. If I'm running any electricity around the part using our coil, then it gets switched to coil. In this case, we stay on the contacts. The next piece is we need to select our current. This is going to depend on the size, shape, and diameter of the part. Now with camshafts like this, in most cases, we're going to see somewhere in the range of around 2,000 amps, which is a lot. In most cases, it takes only a fraction of that to be fatal to human beings and most things that have a heart. So we have to be extremely careful when we operate this machine. Once we have our current control set, all we're going to do is push this magnetic current button and the machine will automatically cycle for the amount of time we've set to run current through the part. Once we've completed that process, we can then bathe the part using our nozzle right here in our iron mixture, and we can examine it with a black light to see what happens. Now, the question is, what do we do when we demagnetize a part? Well, we have to use alternating current, right? So we come back down to the control panel, we're going to switch to alternating current. Now, as a general rule of thumb, whenever we magnetize something, we have to use approximately twice as much current to demagnetize the part. So in this case, if we start at 2,000, we'd end up closer to 4,000 for our demagnetizing cycle. We set to AC, we're up at 4,000 amps, which is quite a bit. And the way that we demagnetize is we're going to hold the demag button until the cycle completes. Now, I say when the cycle completes. How do I tell? Well, up here, we have an amp counter along with a timer that allows us to set the total time that a magnetizing cycle will run. In this case, I can watch my amp counter as I'm hitting the demag cycle, and it'll slowly step down as the part demagnetizes. Again, the reason for that being, as it slowly steps down, we're trying to reduce the current, because if we just switch back and forth, there's a possibility that we can still leave a residual bias on the part, meaning we still have a magnetic pull. But if we slowly taper off the current as the direction is flipping, then we're less likely to leave a bias inside the part. This whole alternating current versus DC, when we're trying to demagnetize a part, you can almost think of as like shuffling a deck of cards. We're just trying to confuse it enough to make sure that there isn't a bias going one direction or the other. You may ask, why does it matter? Why can't we just throw a magnetic part back into an engine? Well, as you'll learn, as you continue on in your studies, if we have a magnet that spins inside of other metal parts, namely coils, then we have ourselves a generator. We really don't want to turn an engine into a generator. There's a few different issues. Number one, the spinning crankshaft inside dissimilar metals could potentially produce a current, which would encourage electrolytic corrosion on those parts. The other issue is, if it is magnetic, any ferrous material that is shed off of other parts as the engine operates are going to be attracted to this now magnetic part, and they're going to collect around that magnetic part, which can cause some pretty catastrophic damage to our journals, our cam lobes, or anything else that would be a polished machine to surface. So that's the quick rundown on magnetic particle inspection. Again, this is something you are not going to do in the field as a mechanic. The reason being, you need a special certification in order to perform these tests anyway. So if you do run into it at some point in time, it's probably going to be because you were trained to do it at your new place of work. Otherwise, this is the process. This is what it can detect. Dye penetrant is a very, very nice way of trying to inspect non-ferrous materials, meaning we can't magnetize it and use a Magnaflux machine. What we're looking for are cracks or flaws or imperfection in the surface that would not be readily apparent to the naked eye. So what we use is this dye penetrant. It comes in a couple different varieties. This in particular is a water-soluble dye penetrant, meaning we can let it dwell in this penetrant tank and then we rinse it off with water. The reason that we do that is as we go ahead and inspect our part over here, this part is going to sit and dwell inside that dye penetrant for a period of time. In this case, 30 minutes for cast aluminum, and we're looking for cracks. And what's going to happen is for the most of this surface, the dye penetrant is just going to sit on the surface. However, in areas where we have cracks, capillary action is going to force that dye to get drawn into those cracks. We have to give it enough time for that process to complete. But once it's done, we can take it to the rinse tank and we're going to rinse it thoroughly with water so that you can't see any dye left on the part. Now, that seems a little counterintuitive, but because of capillary action, that crack is going to retain the dye inside of it as we rinse everything else off. What that allows us to see is only the area that is remaining that has dye left in it, which of course is where the cracks or flaws are going to be. So the way this works, we put our piece into the dye penetrant, we allow it to take its dwell time, which is the amount of time it sits in the dye penetrant, and then we're going to pull it out, rinse it thoroughly, and then we dry it to harden and dry the dye in place. Once that entire process is complete, we're going to take it under the blackout hood and use an ultraviolet light to look at our indication, which is something you'll do when you're in lab. So let's start off. I'm going to grab our case half right here. I'm going to load it into the dye penetrant tank. Process is pretty simple, so I'm going to dip it in carefully, starting with one end. I don't want to let this splash, otherwise it's going to get all over me. Now these studs, it's okay if they don't get all the way inside the dye penetrant. What I really want is for the main body of the entire case half to be submerged completely. That's going to allow the dye penetrant to do its job. Once that's started, I can start my timer for 30 minutes, and we'll revisit this in 30 minutes, give it a rinse, and then put it into the dryer. Our case half has had 30 minutes to dwell, so we're going to pull it out of the dye penetrant. We're going to allow it to drain for a couple minutes, and then we're going to get it into the wash rack to take all of the dye off the surface before we put it into the dryer. So the way we pull this out, again, grab from the through bolts. We're just going to tilt this up as we come out. Now, one of the things you'll notice, there's a lot of passages inside this part where dye likes to hide, and so we need to change the angle on it a few different ways to try to get all of that excess dye out. But what I'm going to do is lift it nice and steadily out of the dye and bring it up on the table, do a little bit of draining. Now this is where gloves and an apron can come in pretty handy. But you can see we're dripping off quite a bit of dye there. I'm just going to turn it this way and try to let some more of that dye run off of it back into our tank. Just like so. And you can still see there's plenty of places where that dye is hiding. Well, thoroughness goes a long way. All right. Rotate this the rest of the way, and I'm pretty satisfied with that. So now let's move it over to the wash rack. Take this part over to our wash rack, trying to avoid spilling it all over on the floor. Drop this right inside and apply a little water pressure. Just want to make sure you get a nice rinse and get all this dye off. All right, finished rinsing, the visible dye is off. So now we can open our dryer and place the part inside. Just like so. Doors close, and we're ready to bake. I'd like to introduce you to the form of dye penetrant that you're most likely going to become the most familiar with out in the field, and that is our aerosol style dye penetrant. Basically, the way this works is we have our penetrant and we have a developer. It's a pretty simple system. The way that this works, after it's been shook up, we make sure the surface is clean from any oil so the penetrant can do its job, and it's going to work just the same as our immersion bath dye penetrant. So the idea is we spray a coating onto the surface we're inspecting, just like so. You get that nice red sheen to it, and we're going to let that sit for 10 to 30 minutes to allow it to penetrate into the part. Once that is done, we're going to wipe off the excess, just like we rinse with a normal dye penetrant solution, and then we're going to apply this special developer, which is going to allow us to see the indication on the part without needing any special equipment. This gets used pretty frequently in complying with ADs for part inspections, landing gear components, you name it. But if you use dye penetrant, this is most likely the kind we're going to see. So let's check back again in about 10 to 15 minutes and see how the developer works. All right, our 30 minutes have elapsed, so now we're going to move on to the developer stage. The dye has had time to penetrate, so we're going to take a rag with some solvent and just remove the excess dye. You can use a solvent to loosen it up, and we can mix it in with another rag to sop up the excess, just like so. All right. The key is we don't want to go too crazy with this because we don't want to try to wipe it out of any cracks that it has penetrated into. So we have to be somewhat cautious to not overdo it. We want to get all the visible red spots off. A little more solvent over here. This nice and clean. All right, so now we can switch to our developer. It's going to be kind of a powdery white substance. Give it a final mix here, and we're just going to give it a couple light sprays. We're going to just give it a couple seconds here to dry up, and as it dries up, it's going to react with any dye that's remaining. So if there's areas where I didn't get cleaned up quite well enough, well, they're going to show up. However, if we have areas that cracked, we're going to be able to see that as well. All right, this developer has had an opportunity to, well, develop as it's dried, and you can see this white haze. Any area where there's residual dye left shows up against that white. So if we were looking for a crack, what we would see through here is a real sharp red line from the area where that dye was able to penetrate into. There's a little bit of sloppiness here because I could have cleaned it up better, but we don't see any cracks, so that would be a pass.